Swayam Prabha. Digital India. Educated India.
In this lecture, we will continue our discussion on the conservation equations of mass, momentum and energy. Let us look at the concepts which we will cover. We will look at mass flow through a control volume, and as we do that, we will look at the mass contained inside the control volume and its fluctuations with time, conservation in a finite space and at a point, integral and differential forms of the conservation equations, surface and body forces acting on a fluid element, and the pressure and viscous stresses. Let us look at the key points of this lecture. So, this gives you the list of key points. Now, let us go back to continuity equation, which deals with mass conservation. Continuity equation. So, you may recall that we started by defining a control volume, a fixed control volume in space of finite extent. And we decided to put that control volume into a flow field. So, these are essentially streamlines of the flow. And if you look at this control volume closely, on its surface, which we call as control surface, you can define small elemental areas, and you can draw the unit normal vector, you can draw the local velocity, and inside the control volume you could draw elemental control volumes. And we discussed earlier that this velocity vector meets the control volume surface at different points, and some places of the control volume it may be entering the control volume, at some others it may be leaving the control volume. And therefore, as you can understand that when it is leaving the control volume, the V dot n would yield a positive value, while when it is entering the control volume, it will have a negative value. It is just because when it leaves the control volume, if this is your unit normal vector, V will point in some direction out of the control surface, and therefore, essentially what happens is the dot product gives you the mod of the velocity, the mod of the unit normal vector, which is 1 times cos theta, which is the included angle. And on the other hand, when the velocity is pointing inwards, then the unit normal and the velocity are pointing in almost opposite directions, and therefore, the dot product will end up creating a negative value. It is because of the cos theta, which will then become negative. So, that is something that we have to keep in mind. Now, when we look at the dot product, it essentially gives rise to the normal component of velocity vector, normal component of the velocity vector. So, you can call it by the name V n, for example. And then if you look at this V n, the quantity V n, it helps us to define a very important quantity, which is the mass flow. So, how would we define the mass flow? Through that elemental area d s, we can define it as m dot, which gives you rho times V n times that elemental area d s, let us say. Okay. So, if you look at the dimensions of these quantities, the density dimension is kg per meter cubed, the normal component of the velocity will be meters per second, this will be meter square, and therefore, if you multiply them, you get kgs per second. So, this is the time rate of mass flow. A related parameter is m dot by d s, which gives you rho V n, and what is that? It is the mass flux. So, instead of the elemental area, if you decide to define it for the complete area, then you actually have to take contributions from all the elemental areas and integrate them. When it comes to mass fluxes, if you involve the different velocity components along the Cartesian directions, then you can define mass fluxes rho u, rho v, rho w, which are along the x, y, z directions. Let us try to integrate the mass flow over the entire surface. So, it is a closed surface which we saw, the control volume has a closed surface, and therefore, we have to include this closed surface symbol when we do the integration. And what do we integrate? We integrate rho v dot d s. So, this is a dot product, and therefore, you will have a scalar coming out of it. So, what is this? This is net okay, let us write it once again. So, what do we get out of this? We get the net mass flow moving out of the control volume. Now, why do we say out? As we explained earlier, that in certain parts of the control surface, this product rho v dot d s will turn out to be positive, and in certain others it will turn out to be negative. So, when you sum up all the effects, finally, you figure out whether there is an effective net mass flow moving out of the control volume or net mass flow moving into the control volume, depending on whether the final quantity happens to be positive or negative. So, this is one aspect of the mass conservation equation. The other aspect of the mass conservation equation depends on the mass content inside the control volume. So, this is the term which gives you the time rate of change of the mass content of the control volume. All right. So, we said on one hand that there is a mass flow rate across the control volume. On the other hand, we talked about time rate of change of the control volume. Now, how do we balance these two effects? Let us try to write down a condition which will balance these two effects. So, we have net mass flow out of the control volume, and out of the control volume means obviously through the control surface, we will call it as CS, let us say, and that should be equal to time rate of decrease of mass inside control volume. So, what we are trying to say is that if there is a net mass flowing out of the control volume, that should lead to decrease of the mass content inside the control volume. And you remember that the decrease would then have to involve a negative sign here. So, put together, how do we mathematically put the things together? Let us try to write down the equation finally, that minus del t rho dV, this is your time rate of decrease of the mass inside the control volume. You are equating it with what? You are equating it with the net mass flowing out of the control volume. So, what was the expression we derived already? For the closed surface, we did rho v dot ds. So, they should be balancing each other. So, if you take the terms together on one side, then it basically boils down to saying so, this is your mass conservation equation, the continuity equation as we say, and this is an equation in integral form. So, we have derived the mass conservation equation in integral form now, involving volume and surface integral. Having said that, we understand that this integral form of the equation is valid for what? It is valid over a finite space, because you have defined a fixed control volume of finite size. It is not infinitesimal in size, that is the point. Now, what about the mass conservation equation if you reduce that control volume to a very small one and shrink it virtually to a point? So, from finite space we want to go to a distinct point in the flow field. Okay. Keeping in mind of course, that the continuum hypothesis still remains valid, because if you shrink the control volume and make it too small, you should not go down to the molecular scales. That is something that has to be kept in mind. So, the point still has a very small extent, which assures that continuum hypothesis is valid. So, keeping that in mind, what we do is we convert the surface integral into a volume integral, and the volume integral looks like this. How do we do it? We do it using the divergence theorem. We have learnt about this theorem in the previous lectures. So, now we are able to get the surface integral converted to a volume integral. So, we have two volume integrals involving del rho del t and the divergence of rho v. How do we come to this term del rho del t? We remember that it is a fixed control volume of finite size, and therefore, you could write the volume integral which we had earlier in the integral form in this manner, because the limits of integration are not changing. This is a very, very important aspect, that for a fixed control volume, you could move a time derivative into the integral without affecting the value. So, finally, for this equation to remain valid, the bracketed expression should be 0 identically at each portions of the control volume, without which you will not be able to reach a 0. If that is the case, then you can write this expression, and this is essentially the continuity equation valid at a point in the flow field. Notice that it is a differential equation. So, from an integral equation we have been able to come to a differential equation. Now, you may be interested to recall what are the assumptions that we made. The assumptions that we made does not restrict the application of this equation much. It is not at all restrictive. You can apply it to 3-dimensional flows, you can apply it to unsteady flows, it can handle inviscid or viscous flows, incompressible or compressible flows. So, as long as it is satisfying the continuum hypothesis, you should be able to apply it to all these situations. Now, if you make one simplification that the flow is steady, then what happens is the time derivative goes to 0, and then there will be a simplification in the equation. If you are writing it in an integral form, it will become like this. If you are writing it in a differential form, it will be like this. So, these are steady continuity equations in integral and differential form. So, this is where we finish our discussion on mass conservation. Let us now start discussing about the momentum conservation. For which we recall Newton's law stating that force applied on a certain mass would lead to time rate of change of momentum. So, in solid mechanics the mass is rather easy to handle, but it is not all that simple in fluid mechanics, and the fluid elements also deform a lot as they move through the flow field. So, you have to keep track of a collection of fluid particles forming that mass. So, there are a lot of complications in handling this equation in a fluid flow. Now, we have to still find a way to apply this equation to the flow which is moving through the finite control volume. So, as we do that, we should be able to work out expression for the force part. So, when we do that, we try to first identify the different categories of forces. We will broadly divide them into body force and surface force. Under the category of body forces, we will keep gravity and electromagnetic forces. These are forces which can act on a fluid element from a distance, while the surface forces act on the fluid element by acting through the surface of the fluid element. So, the two categories are pressure and viscous stresses. So, they act on the control surface. So, this gives us the two categories of forces which act on a fluid element, and then once we work out expressions for these forces, we will then look at how we can evaluate the time rate of change of momentum. Now, if you look at gravity, for example, gravity will not play a role when you are handling low density fluids like gases. So, in aerodynamics we do not care much about gravity, but nevertheless for the sake of completeness you can say that if the body force vector in Cartesian space can be represented using its components f x, f y, f z. So, that is the representation for the body force. So, F essentially is the body force per unit mass, and you are trying to integrate its effect over the total mass contained in the control volume. That is how you would indicate the total contribution of a body force field. Coming to surface force, we will look at the influence of pressure first. So, let us say this shows a part of the control surface, and remember that pressure always acts into the control surface from outside. So, it acts normal and pointing into the control volume. Again remember that if you are looking at the surface normal vector, it points out, and therefore, the surface vector acting over a small element, let us say, would also point out. This would be an uppercase S, because you are dealing with surfaces. Now, in order to integrate the effect of this pressure, of course, we will use a surface integral, but most importantly what we should understand is that over this elemental area, you have to indicate the direction of pressure, and therefore, when you write d s, you write n d s, that is the positive direction outward, while pressure acts along the negative direction, and therefore, we will say that the pressure creates a force of this value with a negative sign associated with it. So, that is the force it is creating on that elemental surface area. Therefore, the sum total force due to pressure would be the surface integral of P d s with a negative sign. So, that is the total effect of pressure as a surface area. As far as viscous forces are concerned, we have to first understand how these viscous forces are created. They are created through viscous stresses, which acting on a particular elemental area create the forces. So, there are two types of viscous stresses, shear and normal viscous stresses. How do we distinguish them? For that, let us draw a Cartesian coordinate system and place a small fluid element in it, a cube. Let us say it is a small cubical fluid element, and then on that, on 3 orthogonal faces, we are going to indicate these stresses, both the shear and the normal kind. The shear stresses will be indicated with taus, while the normal stresses will be indicated using sigmas, and then you can see arrows indicating directions. So, you see that there are a couple of normal stresses sigma xx, sigma yy, sigma zz, and shear stresses tau xy, tau yx, tau yz, tau zy, tau zx and tau xz. Incidentally, these pairs are equal to each other, which are called as complementary shear stresses, and they are equal in order to make sure that moments due to these shear stresses on the fluid element equate to 0. Incidentally, these shear stresses are proportional to the strain rates, which we discussed in an earlier lecture. Additionally, there is a nomenclature associated with all these shear stress directions that we are talking about. So, if we write tau ij, what it basically means is it is a shear stress in the j direction exerted on a plane perpendicular to the I axis. So, we have a j direction and a plane perpendicular to the I axis. So, looking at that definition, if you pick up any one of the shear stresses, let us say tau xz. Now, we were looking at these tau ij's. If you look at the expression for tau xy, for example, tau xy is equal to tau yx, and it is given as del v del x plus del u del y into mu. So, the proportionality constant is mu. It is the viscosity coefficient. In a similar manner, you can write down tau yz and tau zy, which are equal to each other using these equations. So, we will conclude this lecture by saying that we discussed about net mass flow out of a control volume through the control volume boundary or the control surface, balanced by the time rate of decrease of mass contained within the control volume, and the mass decrease or increase within the control volume occurs because of flow field fluctuations as a function of time. The continuity equation was derived in its integral form, which applies over a fixed finite control volume. Subsequently, its differential form was derived, which represents mass conservation at a point in the flow field within the continuum hypothesis. Surface and body forces acting on a fluid element were discussed, and effect of gravity, pressure and viscous stresses on momentum transport was explained. So, with this we end this lecture. Thank you.